Good afternoon, everyone, again. So we are back after the break. For the second half of the Quantum Dots short course, Ilan Jen-La Plante will be the speaker. She's a senior staff scientist at Nanosys, where she leads PL Quantum Dot materials development. And she's been working there since 2016. She has contributed to many of their commercial technologies, including development of bright and narrow heavy metal-free QDs, for the enhancement film technology, for the QD color conversion, as well as for the QD encapsulation methods. In addition to her work at Nanosys, she has also studied the QD nanomaterials at University of California, Berkeley, Ben Gurion University of the Negev, and at Columbia University. So without further delay, let's welcome Ilan and look forward to her presentation. Thank you.
Thank you. Thank you for organizing this short course, and thank you to everybody for attending with your Sunday. I know it's also Mother's Day. So thank you for taking the time to learn about quantum dots here. And thank you to Professor Eisler for her introduction in the first half of this session to the fundamentals of quantum dots. So at this point, you should have a good grasp of what the materials are, what's important about them, how you can achieve that synthetically, how to maximize brightness in films, both in terms of the quantum yield and in terms of the outcoupling efficiencies. So as the introduction was, I have been working on quantum dots for essentially all of my career, both academic and industrial. So they're material that's very near and dear to my heart. And I hope that in the second half of this talk, we can move from the fundamentals to a more industrial perspective on the materials to see how quantum dots can be used on the cutting edge of displays. So in terms of an outline for today's talk, I'm actually going to start with a historical perspective on quantum dot discovery, followed by the current commercial status of quantum dots in displays. And then going back more into the technical side of things, I'm going to talk exactly about which quantum dot properties are most important for displays, what types of display technologies are actually available on the market today, and then which of those displays are coming on the horizon and what we're looking at in terms of research to be able to make materials that meet the needs of those future display technologies. Lastly, I'm going to give a brief outlook on the future trends of quantum dot displays and what you can expect to come in the coming decade after that. So first, a bit of history. Oh, I think that just increased in volume. First off, a history of quantum dot discovery and development, but specifically from the industrial perspective. So this is a particularly important year. In 2023, the Nobel Prize was just awarded to quantum dots as a material. And if we think about the field right now, quantum dots in size and color is somewhat a ubiquitous term. But if you think about how we actually got to where we are today, it's taken nearly a century of work on these materials to bring them to where they are right now. So right now, they're ubiquitous optical materials. They're available in millions of commercial products. But the actual first ideas that seeded the groundwork for these materials started in the 1930s, and that was the first sorts of concepts that the size of a material could affect its properties. And this was a revolutionary idea at the time. Measurements later on, as the decades passed, started to actually observe that this was true. And some of the first work in this was in the field of thin films. This is as the semiconductor industry started to develop. And you can see that in the 1960s and 80s, there were actually the first laboratory measurements of quantum size effects. In terms of quantum dots moving from a concept to an actual proof of concept for the materials, this first happened in the 1980s and 90s. And the really groundbreaking discoveries that were made in those decades are recognized in the 2023 Nobel Prize in Chemistry, which was awarded for the discovery and the synthesis of quantum dots. So it's not just their existence, but actually being able to make them. So one of the first landmark discoveries was Ekimov's demonstration of quantum size effects observable in copper chloride nanoparticles embedded in glass. So these are not the types of materials that we typically think of in terms of optical emitters, but it was the very first time somebody was actually able to create one of these quantum confined materials in a laboratory setting. It was during a time period when science was very separated across the globe. So there were also other studies that were happening across the world away, and these were in the laboratory of Lou Bruce. This was at Bell Labs at the time, and scientists there first made nanoparticles that exhibited quantum size effects. And in this case, they did so floating freely in a liquid. So this is closer to the types of nanocrystal syntheses that Professor Eisler was describing earlier. So that pioneering work between these two different groups essentially marked the birth of quantum dots as a distinct field of research. And it sparked an incredible amount of interest across the scientific community in being able to study these materials now that it was possible to actually make them in the labs. As was described in the first half of this talk, the physical size of the material is absolutely essential to its properties and its performance. So to be able to actually control the size of the crystal size is just as important as being able to make it. The third recipient of this year's, or last year's Nobel Prize is Mujib, professor at MIT. And his contributions here had to do with new and innovative synthetic methods to be able to make very precise size controls of these quantum dot materials. Moving beyond the Nobel Prize, to actually be able to take this material and bring it all the way to the industrial status that we know it today, there were years of work, both from academic labs and industry, to be able to expand the field and demonstrate the impact on science and humanities. Typically, the Nobel Prize is not awarded just for discovery. It isn't until it's actually demonstrated its usefulness out in the world that it's a retrospective in terms of awarding the initial discovery. If you consider the time period after the initial work in the 1980s and 90s, you can break apart the remaining decades into essentially two major blocks of time: a discovery phase and a development phase. In the discovery phase, there was heavy emphasis placed on expanding the chemical synthetic methods to actually make these materials. So some of this individual work that I was describing that happened in Lou Bruce's labs took place also with postdoctoral fellows Paul Vasados and Mujib. And both of these scientists then spun out and created their own research labs as they started their academic careers as professors, Paul Vasados at UC Berkeley and Mujib at MIT. And during the 1990s, there was huge emphasis placed on creating new synthetic methods to be able to make these materials, control their properties, and test some of the early initial applications of them. So in terms of electroluminescence, the very first studies actually came in the 1990s as people started to explore what was possible with these materials. Very shortly after seeing the immense potential commercial implications of the materials, Nanosys, as a company, which is where I work, was founded, and some of the co-founders, the scientific co-founders, were in fact professors Buendi and Vasados, who continue their interactions consulting with the company to this day. So combining scientific, engineering, and business backgrounds, Nanosys has actually invested more than 2 million work hours of time into being able to bring this material forward. And with these materials, once they were brought to product grades, it was possible to scale up these materials to mass production and release some of the first applications, which I'm going to talk about today. In terms of releasing commercial products with quantum dots, a major breakthrough happened in 2013. This was the first commercial launch of a quantum dot containing product. This was done by Nanosys, and this is with QDEF. It happened in the Amazon Kindle Fire. This was our very first quantum dot fab coming up at the same time. This was being certified in Milpitas, California, where our headquarters and research still are today. This first product came out. Consumer reception was huge. So the following years saw a lot more Nanosys firsts as more and more quantum dot containing products with SKUs came out onto the market. So you'll see as you move along this timeline, the first QDEF monitors, the first QDEF notebooks, and then ultimately heavy metal-free quantum dot TVs and quantum dot LCD TVs for automotive applications that were released over the years. To keep up with this increasing demand, Nanosys doubled their manufacturing capacity. This came up to 50 tons per year in late 2019. And we actually began a collaboration with Shoei Chemical to be able to keep up with the market growth. Product innovation has continued between 2019 and today. There are now more than 1,000 different product SKUs that contain quantum dots out on the market. Right now, 100% of mini LED TVs are using quantum dots out there in the market. And quantum dot OLED TVs, which launched recently, are hugely popular and proving finally that quantum dot versus OLED is not a zero-sum game, and there's a lot to be gained from combining technologies out there. Last year, we celebrated the Year of the Quantum Dot, which is the 10-year anniversary of the first release of QDEF and the release of the Nobel Prize. And it's really a history that we're proud to be part of. As of today, you can see that Shoei Chemical has acquired Nanosys, or all of the quantum dot business of Nanosys in 2023. And they've actually just started the world's largest quantum dot factory in Itoshima, opening this March. So how did we get from Nobel Prize winning research in a lab to being able to make the world's largest quantum dot fab in existence? So in the early 2000s, when Nanosys first started, there had been huge advances in quantum dot synthesis, but all of the work that had taken place was exclusively at the lab scale. So when you talk about lab scale research, you saw the images in Professor Eisler's talk earlier. You typically think of illustrations like what you see on the right side of this slide. You see glass flasks, syringes where you're injecting chemicals. Typically, these are run under inert conditions, so you run these on things called Schlenk lines, where there's nitrogen and vacuum attached to your flask. And the typical reaction scale in a laboratory synthesis produces something on the order of 10 to 20 milligrams of quantum dot material per batch. So not only are these scales certainly very small when you consider them, the early reproducibility of the results that you were able to get in settings like this were also quite challenging. There were a lot of batch-to-batch variations that people had, and a lot of different sources for this variety in outcomes. So some of this has to do with the chemical purity of your precursors, if you have any contaminants that are reactive in the system. And some of this actually has to do with setup to setup differences. So it could be differences in the heating rates of your system, mixing rates. You're talking about very finely controlled crystal nucleation. So it can be sensitive to all of these things, and in addition, operator to operator variations in how someone might actually handle their chemicals or be able to do certain steps at certain speeds. So since, again, the unique power of quantum dots is that their size dictates their electronic properties, any variation in the chemical reaction that causes differences in size is super undesirable and has impact on the final results. So how did we move past this state? So in addition to the scale and reproducibility issues, there were also very specific material challenges to overcome to make a quantum dot that's ready for a commercial product. So there are a lot of different semiconductors out there in the world. You can make quantum dots of most, if not all of these. But two of the primary candidate materials for quantum dots that emit in the visible wavelength range are cadmium selenide and indium phosphide. So I'm going to describe some of the history of those syntheses here. So for cadmium selenide, the early syntheses that were out there typically relied on toxic and highly reactive organometallic precursors. One of the common ones that was used in those initial works was dimethylcadmium. And they were successful in providing the reactivity necessary to generate crystals at lower temperatures, but the extreme reactivity of those precursors typically led to reactions that were difficult to control. A major advance in the synthesis of these came as those early precursors were replaced with ionic species, and that led both to greater reaction safety and also greater reaction control. So as Professor Eisler explained earlier, single materials, just cores like cadmium selenide, can be emissive, but it's much more advantageous to grow something like a core shell structure. This is to maximize brightness, and in addition to maximizing brightness, you can also improve particle stability and reliability. So early shell chemistries that were developed were not sufficient to produce product-ready quantum dots. And some of these difficulties had to do with internal crystalline defects. And part of that had to do with the shelling precursors and reactivities that were available at the time. So initial shell chemistries were often run at very low temperatures, So low temperatures in solution are something like 150 to 200 degrees. And it wasn't until later that these precursors were replaced with more stable precursors, which you can actually bring the entire reaction up to a higher temperature and produce improved crystalline uniformity in the system, higher quantum yields, and better particle stability. I'm going to get into this later in the talk, but overarching through this entire time period, there had been pressure to find a heavy metal-free alternative to cadmium selenide. So cadmium selenide was the first material that was demonstrated in those Nobel Prize-winning discoveries, and it's incredibly useful because of its band gap and its emission in the visible wavelength range. But there was huge pressure to find an alternative, and one of those early alternatives that did turn out to be quite successful was indium phosphide. So starting in the early 2000s, research on this material system started, and in some ways it was successful in the sense that you can create a material which is emissive in the visible wavelength range, but there were a lot of challenges that came with this. So the early synthetic methods that we saw for the growth of those cores yielded quite poor size distribution, so incredibly broad full width at half maximum, which is not a good property for displays. There are also fundamental differences between indium phosphide and cadmium selenide in terms of how the crystal grows. You can consider a material like cadmium selenide to be more ionic in nature, so more unequal sharing of the charges in the bonding, whereas indium phosphide is more traditionally, like semiconductors that are grown at higher temperatures, a covalent system, so more equal sharing of the charges in the bonds. And chemically, it's much more difficult to produce crystals at low temperatures of these covalent structures, that it typically requires much higher reactivities. So the combination of these create a lot of early difficulties in the system. Likewise, the types of shells that you could grow on indium phosphide were insufficient to produce the types of quantum yield, brightness, and stability that were needed for these commercial products. Since that time, we and others have invested a lot of work to correct all of these concerns, finding new chemical precursors to grow the cores, new shell chemistries, and understanding what it takes to create the correct types of crystal interfaces between the shell and the core. If you move to where we are today, the size distributions of indium phosphide quantum dots can actually rival those of cadmium selenide. So if you look on the diameter basis of your size distribution of your materials, you can make indium phosphide that is just as narrow in its size distribution as cadmium selenide. And this is really decades of hard work from scientists, both industrially and in academic labs across the world. In addition to being able to control the size dispersion, the root causes of batch-to-batch variations have been identified and controlled. Some of this, again, has to do with the chemistry of your precursors, and some of this has to do with your reaction equipment itself. So at the industrial scale, we are actually able to produce lot after lot of conforming material. So what I'm showing here in this graph is a process capability chart for material. In this case, these are syntheses of red indium phosphide quantum dots at 100 kgs of quantum dots per lot, so incredibly large scale. In this case, we're targeting a center peak wavelength of 628 nanometers to achieve red, with an allowable upper and lower standard limit of 2 nanometers, and you can see that all of these 24 lots are conforming. I think my microphone, okay, are conforming within the limits that are set. So again, at their very heart, controllable emission spectra are what makes quantum dots such a revolutionary optical material and gives them so much power in displays. And based on the electronics of color coding, the way in which we run displays today is with blue, green, and red channels that we recombine to create the rest of the colors of the display. If you compare quantum dot emission to older styles of emissive materials, in this case I'm showing a YAG phosphor in the gray spectrum, you can see that quantum dots, if you, well, I don't think, well, half of this graph is not showing, but typically there would be another graph that's also shown on this where you can see the emission spectrum of the blue backlight LED with that of the green and the red. And specifically what you'd see in that graph is that the number of photons which fall very specifically within the green and the red channels are maximized for quantum dot emission as opposed to phosphor emission. I can see it on my screen. I think it's just the contrast of why it's not there. So it seems like a simple difference between having all of your photons fall within those color channels or having them be broadly distributed, but the impact is actually huge. So first of all, it impacts the energy efficiency of the system. If you have any photons that are off the desired wavelength, those would be typically filtered out if you have color filters. So it's not just that you're incapable of recombining your spectrum to form the colors that you want, but if you have to apply those color filters to remove out the photons that are being generated at undesired wavelengths, it's a huge efficiency loss to your system. The second is obviously that if you have any spectral bleed through of wavelengths off of your color channel, you're going to decrease the number of colors that you can reproduce from those three channels of blue, green, and red. So peak wavelength is one thing that's important, quantum yield is the other. Professor Eisler covered this very thoroughly in the early parts of this talk. The thing that I wanted to highlight from the industrial perspective is that she had referenced that there are multiple different measurement methods of how you can quantify the quantum yield of a material. You can have dye reference material. You can have direct photon counting where you look at all of the light that's absorbed versus all of the light that's emitted. And you can also have heat loss calorimetry. And what I wanted to highlight here is that if you consider these different techniques, some of them do, in fact, have higher measurement accuracy. The highest is from this heat loss calorimetry. But you also pay the price of the difficulty of the measurement. And for typical industrial usage, most measurements are actually made with this photon counting method, where you measure the absolute quantum yield of the material, that it has a good balance between the ease of measurement and the accuracy that you get from that measurement. So in an ideal world, quantum dots can actually achieve quantum yields of 100%. And there are many documented cases of this out there in the literature and also now in industry. Practically speaking, the ways that you get this is through careful engineering of the core, the shell, and also ligand structures. So in the simplest case, you just have one core material and one shell material. In reality, you can have very complicated systems. You can have layering of 2, 3, 4 materials. You can have alloying between those layers. You can create very tunable changes in the crystal structure and the band alignment of the core and the shell. So 3 key considerations of how to grow a shell that leads to the highest quantum yield possible. The first is that the shell is grown epitaxially onto the core. So what I mean by epitaxially is that the shell material has to adopt the underlying crystal lattice of the core underneath it. This is important to maintain the perfection of the bonding at the interface between the two materials. The second is that when you grow that selected shell material, it needs to have a similar crystal size and crystal structure to be able to minimize internal defects. That if you have any sort of point defects or missing bonds at that interface, you can lead to an electronic defect in your system, which can decrease the emission, the quantum yield of the system. You can essentially create a non-radiative state that your excited state can pass through. Lastly, I think this was already highlighted that the best types of protection that you can get are if your outer shell is with a wider band gap than your core material. And this can be very difficult because the number of materials that are out there to choose from are limited when you consider these 3 different requirements of the system. So all in all, we can put these things together to be able to produce really high quantum yields. And again, quantum yields are not just important for efficiency and for brightness. The stability of the material, or how it does when you actually use it later in a product, is super impacted by that quantum yield also, that you want to maintain as much of your emission through this radiative channel to prevent degradation later on. So in terms of colloidal synthesis, this is specifically what was highlighted in the Nobel Prize. It's not quantum dots made in any sort of way. It's quantum dots made in solution. So the benefits of making quantum dots in solution are control of the materials, but it's also about the cost and manufacturability. That if you consider traditional semiconductor fabs, where the materials are grown in the vapor phase, you're actually quite limited in how much material you can make. This is done directly onto an existing wafer. And if you consider how much it would take to make 1 gram of quantum dots, I think I was describing 100 kilogram lots before, to make 1 gram of quantum dots, if you were to do it in the vapor phase on wafers, you would need more than 50 square meters of wafer material to be able to do this. So moving into the solution phase, this is an actual photograph into a reactor. It enables us to use more traditional chemistry fabricating methods and to bring these up to the scale required to be able to address an entire market. If you consider that same gram of quantum dots, what it would take in solution is something on the order of a liter or less of solvent. Again, the inorganic portion is some of the system, but the organic and/or inorganic ligand sphere is just as important. So on the outside of this particle, it's not just a tiny rock floating around in the solution. You have a lot of versatility in what you put on the outside. So some of the benefits of what is on the outside of these ligands are what was described in the first half of this talk about passivating surface states, increasing your quantum yield. But the other half of the system is the flexibility of what you can do with those ligands on the surface. So you can imagine 2 different control points. You have control over the type of chemical bonding that you have from the ligand to the inorganic portion. And you also have complete control over the main component of that ligand molecule itself. You can tailor its chemistry, you can tailor its solubility to be able to formulate in a lot of different types of applications. So in actual product work, you would need to be able to bring these quantum dots into different solvents, into reactive monomer systems or resin systems, inks and photoresists, and sometimes you would actually want to very specifically target and place quantum dots. And you can even do reactive chemistry on the far end of your ligand to be able to bind this to particular sites and surfaces. So at the end of the day, you have the electronic and optical properties of a semiconductor, but you have all of this in full liquid processable solution. So the chemistry and the material science is one half of this, and then the entire other half is actually being able to produce these at the scale that you need to be able to fabricate products. So if we look back at the history of quantum dot production that we've done so far, first starting at Nanosys and now expanding, you can start imagining how we came to this, first of all, from the lab perspective, right? So we're used to working with this glassware. You can heat, you can cool, you can keep it inert as you're doing your reaction chemistry. There is a maximum scale that you can operate at inside glass flasks. You can bring this up in scale. Probably the maximum you can get to is about a 30-liter reactor in glass. So to be able to go any further, there had to be a lot of innovation and ingenuity from the engineering side. So not only was it necessary to have chemists to be able to design these materials and the reactions to make them, but we also had to couple this with the engineers who are able to recreate the reaction conditions that are possible in the lab at a larger scale. So going from these flasks, the next scale up, you would need to have an actual reactor. And if you come to the labs and you see what this looks like, it honestly looks similar to a brewery in the sense that you have these giant tanks that you can heat, you can cool. But there are considerations that are very important to the reaction chemistry. So some of these are the transfer rates, the mixing rates, and the heating rates in the system. So all of these have to be super tightly controlled and have to be incredibly fast in some cases. So there's a lot of engineering that comes behind this. Initial reactors were a start. It's a proof of concept. You could definitely make the materials. But as demand grew out there in the world for more and more products that contain quantum dots, it was necessary to bring these up to scale. So you can actually see the largest scale that happened at California, which is a 2-story reactor. So you can see that there are 2 operators here. The reactor goes all the way down to the bottom floor below. And there are actual full winches to bring chemicals up to higher levels to introduce them into the reactor, and dedicated transport and flow lines to the systems. So today, I had already mentioned this before, but as of 2023, first starting as a partnership and then an acquisition, Nanosys and Shoei Chemical are one. And this has really brought quantum dots to be an entire global endeavor to be able to supply the full market that's out there. So quantum dot R&D continues at our site here in Silicon Valley. This is where I work and many who work in our R&D department. But now we also have expanded production. This is in 2 different locations. First of all, in Tosu for production engineering, quality assurance, and also more R&D. And then very exciting, recently opened is a second plant at Itashima. So this plant at Itashima is the start of the world's largest quantum dot plant in operation to date. The upper illustration here is the concept design of the building, and the fab is now up and running, so this is a true photograph of the plant. This is from March 2024. Lines are up and qualified. Material is being produced in the system. So this is super exciting to have this come up in line today. Based on the lines that are operational right now, there's the capacity to serve 40 million units of televisions per year, which is a huge capacity. And the way the building was designed here actually keeps the possibility open to expand the capacity 8 times this, so nearly an order of magnitude higher as demand is there. Okay, so that's the historical perspective on the materials and how we brought them to the commercial scale that they're at currently. I wanted to get into next what the commercial status of quantum dot displays look like. So what sorts of materials are out there, and how are these displays being received? So first of all, on the material side, as I described, there are a lot of different semiconductor materials out there. You can make quantum dots with all of these. But if you consider the periodic table, there's actually a fairly small zone in which those elements can be recombined to make semiconductors. So this is essentially the palette which we are able to work with when we're designing the materials that we want to work with. The 2 key players out there today are cadmium selenide and indium phosphide. And the main consideration for both of these are that their bulk band gaps are near the visible wavelength range. So cadmium selenide at 1.7 EVs, sort of in the deep red, and indium phosphide at 1.3 to 1.4 EVs is an even slightly smaller band gap. But both of these, as you quantum confine the system and you push that band gap up, can easily achieve wavelengths across the full visible range. The next consideration is the shell materials that you can grow. Again, these have to be band gaps that are larger than the core material that you choose. And you also need to consider what types of crystal structures you can make of each material and whether the size, so the spacing between atoms in the crystal, is similar or dissimilar between the systems. In terms of material that contains heavy metals or not, among the common core and shell materials that I've shown here, you can consider that cadmium selenide and cadmium sulfide are 2 which both contain cadmium and are typically used in core shell structures. So if you consider what's possible with indium phosphide, you're exclusively limited, in this case, to shells of zinc selenide and zinc sulfide. And you can already see that there's a difficulty here, that these materials do not have the same lattice spacing between them. So there's a lot of work that has to be done to be able to make the core and the shell completely coherent across the system. These are what's commonly commercially available today, but there are a lot of other materials that are potential in the world. A lot of research groups are looking at perovskites, specifically lead halide perovskites, which are a new class of materials that people are looking at. They exist in the bulk, and people first started looking at these for solar cells, and they've been incredibly successful at achieving super high efficiencies in solar cell systems. People are also looking at them for their photoluminescent properties. You can see commercial work from Avantama on this. The main concern here is all of the emissive materials that have been identified so far do contain and rely on lead in their system. So lead is a regulated material in there, and it exists at concentrations that are quite significant in the system. So it's of interest, but it's not yet clear where this will fall in the commercial landscape. Another material that's of interest has to do with structural control of a material, so quantum dots are not just these spheres. Professor Eisler described some conditions in which case you may be interested in forming a different type of structure besides a sphere. Cadmium selenide and cadmium sulfide are materials that it's been demonstrated that you can form these nanoplatelets. So it's possible, instead of confining the material in all three directions, you actually just confine it in one, and your excited state can spread laterally across this plane. They're interesting because of these unique optical properties that you can get from them. But again, their control and what we've been able to achieve with them commercially has been fairly limited so far, so you're not going to find a lot of these out in the commercial world today. Another material that's out there are these 136 type systems. There are a lot of materials that fall under this designation. So there's SIGs and CIS. You'll hear these often, again, from the photovoltaic industry. People use these materials for their controllable band gaps. They're particularly interesting because the amount of alloying that you can get between these different element compositions means that there's a lot of tunability in the band gaps that you're able to achieve in the system. Commercially, there have been demonstrations of these as a down converter. So this is agricultural film demonstrated by Ubiquity. But you're not going to often see them in display applications. And that's because the nature of emission that you get from these systems is very, very broad. That the type of emission does not come directly from a band gap transition, but rather relies on defects that are in the structure. So there's a lot of variation in the absolute emission wavelength of the system. If you consider heavy metal-free quantum dots specifically, many applications are still seeking those. First of all, there are all of the wide bandgap blue emitters that for photoluminescent down conversion applications, what we need are green and red quantum dots. But for many new up-and-coming applications, which I'll describe more later in the talk, we are looking for blue emitters as well. So in terms of the best blue emitters out there, most of these are based on the zinc chalcogenides. So these are zinc selenide, zinc telluride, and zinc sulfide. And these are very similar to the cadmium chalcogenides, but with much wider band gaps. So you consider building up core shell structures of these very similarly to the cadmium selenide system. There have been some documented demonstrations, and this is a very exciting new field that's out there. I had already described 136 materials with very broad emission band gaps. It has been documented, and it is possible in very specific cases to see band edge emission from these materials. So there's a lot that's potential in this system in terms of commercial application coming up. Many people are looking for lead-free perovskites. This is a field a lot of academic groups are looking into. It's not clear where this is going to go yet. There's a lot of potential. At this point, the PL efficiencies are incredibly low and the materials are not very stable. So at this point, you're not going to see these yet, but it's certainly an area to keep an eye on. In terms of materials that would be most exciting to see come out, we are specifically looking at the nitride. So if you consider micro-LEDs or traditional solid-state emitters, almost all of these are based on nitride systems. Fully tunable across the visible wavelength, very difficult to make colloidally. So the types of chemistry that you need to make these, when I was describing the differences between cadmium selenide and indium phosphide and going from an ionic crystal to a covalent crystal, you can imagine the nitrides as being one step further in that. So the types of gas phase reactions that make solid-state nitrides are all incredibly high temperature. And finding the types of chemical precursors that are possible to use in solution at lower temperatures has been a real challenge. So it may come, but right now it's still very much in the R&D phase. So overlaying this entire topic of what materials people would like to use for quantum dots, there is external regulation that happens as well. And this has been a story that's gone along with the scale-up and commercialization of quantum dots. So the EU passed quite some years ago a restriction, people colloquially refer to it as RoHS, but it's a restriction on hazardous substances. And for a long time, there had been debate and there had been extensions of these exemptions. And finally, I think we're coming towards the end of this story. So at this point, the EU Commission did adopt a new directive for RoHS. So at this point, what they're recommending is that all exemptions expire in the coming years. There has been a redefinition of what type of quantum dot containing application it is. And I'm going to describe the different types of quantum dot displays later. So in some specific cases, there's been an extension that can allow more cadmium in direct color conversion applications, but this is also something that's expected to expire moving forward. So at this point, the full restrictions of RoHS are expected to take place over the coming years. There is still the possibility that there could be a renewal to that exemption. So there is right now a timeline for when the new regulation would go into effect and when any exemptions would roll out, and I think that's an 18-month rollout period for this. But there is the possibility for requests for extensions of that. So in terms of the commercial perspective of these two materials, of cadmium selenide and indium phosphide, it's actually somewhat of an anticlimactic ending to this debate and story. So some manufacturers will prefer to use cadmium selenide-based materials, some will prefer to use indium phosphide-based materials, but at the end, by actual law and regulation, the final definitions have been that cadmium should be kept at 100 parts per million or lower in a homogeneous material component in a display. So at this point, when you consider the types of applications that are out there with Nanosys quantum dots, all of these are actually, in fact, RoHS compliant. So all of these contain concentrations of cadmium in the homogeneous layer that are less than 100 parts per million in cadmium and do not contain any lead in the system. So as of March 2023, new regulations went into effect. You'll see products labeled with this no cadmium symbol, which indicates that the concentration of cadmium is less than 100 parts per million. So this is the current status in terms of regulation. And again, these laws apply to Europe, but many display manufacturers prefer to make a consistent product across all markets instead of differentiating into different systems. So quantum dot TVs are very common today. So in 2013, I was describing the very first commercial product containing QDEF. At this point, they are incredibly ubiquitous and very, very well received. So 70%, if you go not just to consumer purchasing, but to actual review websites of televisions, more than 70% of the televisions reviewed by Ratings in spring 2024 contain quantum dots in the system. Similarly is true for Tech Radar. These are multiple different brands that are out there, multiple different types of quantum dot displays that implement quantum dots. So it's not just QDEF anymore that's out there. And it's also different material types. So it's indium phosphide, it's cadmium selenide, and blends of the two of those. A fun thing for us to see actually was that in 2023, the Nobel Prize was not the only award for quantum dots that came out. There was actually an Emmy Award. It's not the Emmy Awards that go to actors that you may know of, but there is a series of technical Emmy Awards. And one of these actually went to the display manufacturer Small HD for their lineup of monitors, some of which include QDEF in the system. So if you see this scene, this is from the filming of Dune. Here you see the director, Denis Villeneuve, and he has one of these monitors here. There are actual quantum dots on that set of Dune being used. And the importance there, again, is that having filmmakers be able to see full color rendering on the spot is super important to understanding that the content that they're creating is as they desire the vision to be. So at this point, since 2023, starting with that Amazon Kindle Fire, basically all of the world's major brands have adopted quantum dots into some part of their lineup. So from 2013 to today, all of these different brands have launched product SKUs. And if you look at the total shipments, this is now greater than 70 million units of quantum dot containing displays that are out there. If you consider where those quantum dots are coming from, materials coming from Nanosys Shoei are the preferred supplier for almost all of these. So if you consider the green and blue bars of these supply charts, of the SKUs that are out there containing quantum dots, almost all have come from either Nanosys or Nanosys partnered sources that are out there. And this again has to do with the really tight control of the quality and the properties of the materials themselves. So that's what I'm going to talk about in the next section. What is it about quantum dots and their properties that makes them particularly suited to displays? Why are those displays being received so positively and viscerally by consumers that are out there? So the easiest overview of this is that there are 3 primary advantages to quantum dots for displays: pure colors, high brightnesses, and really fast response times. So in terms of pure colors, the narrower you can make that emission line width, and having incredible tuning control over the exact peak wavelength means that you can target very, very specific wavelengths to recombine, and you can recreate the maximum number of real-world colors in your actual display. Number of colors is not the only consideration. Your material needs to be able to operate at really high brightness. Quantum dots are able to do this. So something beyond just color is experienced color range and color volume. I'm going to describe those a little bit later in this section. And then lastly, due to their strong quantum confinement, quantum dots have incredibly fast radiative rates. So after you excite the system photoluminescently, it emits that photon, that green or red photon, really, really fast, on the order of tens of nanoseconds. So if you have really fast response rates in your material, you can get very crisp and responsive displays back out of that. It's super important to flat panel displays, but also important to potential future applications like AR and VR to prevent cyber sickness, that you don't want ghosting or any sort of delay in when you see color in that. So I'm going to go into each of these sections in more detail. So first up, about color. The main way in which we're going to look at this are through these chromaticity diagrams. So this one here, it's the definition from 1976. And what you're seeing in this graph is a representation of all of the colors that humans can see. So there are obviously more wavelengths of light that are out there, but these are based on research and measurements of where human perception actually is. And within this graphical representation of color, there are a lot of what we call color spaces. So it's regions within all of these potential colors that are considered important. And the 3 that we're going to look at here specifically are Poynter's gamut, which is on this slide, and then also DCI-P3 and REC 2020 to explore their characteristics and how they relate to each other in the grand scheme of color representation. So Poynter's gamut is the ultimate goalpost. It was measured by going experimentally and measuring color that's reflected off of real-world objects. So humans can see more colors than this, but this is actually what is out there in terms of reflections typically seen in the actual environment around us. This was done in the 1980s, and it stands as a theoretical concept that we use to benchmark other color reproduction endeavors. There are colors that fall outside of Poynter's gamut. So Poynter's gamut here is measured, these yellow dots of those actual measurements. There are colors you can see that fall on the outside of this. Humans can see them. You'll see things like light coming from particular LEDs or color graphics, and those are outside of Poynter's gamut. So it's not necessarily part of recreating typical real-world colors that are out there, but it is something that some displays would like to demonstrate in the future. Flipping between these slides, we're moving on to the next color space. You can see highlighted in this gray triangle around here is the definition of DCI-P3. So DCI-P3, it's not an official standard, but it is something that's been adopted by the digital cinema industry. That's what the DCI stands for. And it's something that they commonly reference to. If you compare it to older color standards, it covers nearly 85% of Poynter's gamut, so this covers most of the real-world colors that are out there. And until there is a formal industry standard, many in cinema have adopted this as their current color, target color gamut. So you'll see a lot of displays reference what percentage of this particular color space that they're capable of reproducing. The next color space here is broader, so if you flip back and forth between these, you can see that the gray triangle is expanding. The next typical color space that people will reference a lot is REC 2020 or BT 2020. It's a recommended standard to move to. It has not yet been adopted. You can see that it covers 100% of Pointier's gamut, so all of these real-world colors would be encompassed within the Rec 2020 standard. It is currently used for ultra-high definition TV in terms of their coding for it. And it's something a lot of people in 4K HDR content are referencing. So you'll also see displays right now quantifying what percentage of BT 2020 color space can be recreated by a display. How does the display actually create this color gamut? In the ideal case, your subpixels of R, G, and B would sit on the very outermost axis of this diagram. So this curved axis that's here represents monochromatic light. So it's wavelengths from blue to red with 1 nanometer line widths on the outside. So in the perfect world, you would have your green and your red and your blue sit on the very, very outsides of this axis, and you would be able to recreate this full color space with those wavelengths. In reality, most colors are polychromatic. I mean, there are no typical sources that have 1 nanometer wavelengths. As you have a broader line width, as your color is more polychromatic, you would imagine that these sources would move inwards on this color diagram. So the full area would not be covered as you increase in line width and move closer into the center of this diagram. In reality, the true color of each subpixel is a combination of the line width of the emitter and also any color filters that are used in the system. So both of these are key contributors to the final color gamut coverage. So specifically for BT 2020, you would want your 3 color primaries to be at these particular wavelengths. For blue, you would want 467 nanometers, green 532 nanometers, and red 630 nanometers. Again, the broader you are, the further inside this diagram you fall. So what does this look like actually for quantum dot materials? Again, if we look at our 2 common materials, cadmium selenide and indium phosphide, the line widths of these are not monochromatic. They are not 1 nanometer. If we look at mass manufactured materials, it's possible in the case of cadmium selenide to achieve line widths as narrow as 18 nanometers, full width at half maximum. And this is actually getting to what Professor Eisler was describing as the homogeneous line width of the material. So this is not that your quantum dots are different sizes from each other. A singular quantum dot has a line width of about 18 to 20 nanometers. This has to do with the phonons in the system, electronic state splitting in the system, that even if you were to improve your chemical synthetic techniques, you cannot get your line widths much narrower than that. For indium phosphide, these are broader, and there is a ways to go still. Chemically, if we look at these, there's been a huge advance in the chemistry of doing the nucleation. The absolute size distributions are quite similar today between cadmium selenide and indium phosphide, that the nucleation chemistry is there, but earlier we talked about the band gaps of these 2 materials. Cadmium selenide is at 1.7 nanometers, EV. Indium phosphide is at 1.3 to 1.4. So if you go back to thinking about that diagram of the strong and weak confinement regime, for indium phosphide, you're sitting there very much in the strong confinement regime. So if you have the difference of a few atoms on an indium phosphide, you're actually going to have a greater difference in the band gaps that you're seeing. So overall, this makes it fundamentally more difficult to achieve narrow line widths with indium phosphide. So you would need to have an even narrower size distribution in the system to match that of cadmium selenide. In addition to the line widths of your material, these are coupled with wide color gamut filters, and these are just as critical. So to date, it's possible to be in the 90% coverage of BT 2020 color space with quantum dot systems. Right now, today, 100% of premium televisions are targeting wide color gamut color experiences. So it's incredibly popular in terms of what consumers are looking for on the premium end of display. Right now, quantum dots cover part of this. So right now in 2023, They cover more than 50% of those premium televisions that are targeting wide color gamut coverage. And they're anticipated to continue to grow as the years come to eclipse a greater than half market share compared to OLED products as we move forward. So the hope is that these wide color gamut color experiences that people are finding very enjoyable on the premium side of things will someday be able to come to the mainstream market, so to televisions across all price ranges. So what does that look like in terms of which televisions are or are not covering this wide color gamut coverage? We can break this apart into two different methods of measuring this. In one of those cases, you can look at what percentage of display areas are covered with wide color gamut coverage displays. Right now, it's less than 30%. So there are quite a bit of area still left that is not delivering these high color gamut experiences. Similarly, you can look at this in terms of product revenue, and there's at least 60% of the market that is not yet addressed with a wide color gamut coverage display. So the first part of this has to do with color. The second part combines the concepts of color with brightness. And there's a difference here. If you consider color alone, that does not fully describe how humans interact with the displays that they see. So particularly, there's a lot of color theory that has to do with how people perceive brightness when it's combined with color saturation. So if you look at these color chips here, they're actually all at the same luminance in terms of nits or brightness. But to a human, most people will consider that the more saturated colors appear brighter to them. And this is a documented effect in how humans perceive color saturation. So one of the desires here is that it's important to look at not just color gamut coverage, which I've described as this 2D representation of color, but to consider other metrics and metrologies for looking at how people actually interact with their displays. That a lot of those studies that I was showing before came from the 1930s, the 1980s, and we understand a lot more about people. So one consideration here has to do with experience color range. I think this is still an area of debate of how people want to quantify and measure these systems. So in this concept of the metrology, you would have not only color, but also its luminance and how you quantify the colors that are represented in a display. The other concept that's here besides experienced color is color volume. So you'll see this described in other calculations. A lot of these studies came out of Dolby laboratories. And you can imagine, again, if you look back on the original chromaticity diagram that I was showing, you could see a particular pixel of a display and imagine that its color is indeed represented in the color gamut space that was covered. But for particular scenes, that color needs to be very, very bright as well as saturated. And in those conditions, it may actually fall out of the capabilities of display. And this is something that you can see if you consider color volume and not just space. So color volume, again, would consider the chromaticity on two of the axes of the system, and brightness or luminance on the other third axis of the system. So again, this is something that's being debated of what the best methods of measuring this are. If you come by our booth in the expo, there's actually going to be a demo on it to do with live measurements of color volume from displays. So the third aspect here is an advantage of quantum dots for displays, and again, that's their exceptionally fast radiative rates. So it's possible for quantum dots to respond in nanoseconds, which is essentially instantaneously to the human eye, to changing excitation light, so to exciting the system with a higher excitation wavelength. In contrast, typical narrowband phosphors that are out there today, things like potassium fluorosilicate or KSF phosphors, the red component is a lot slower, and it needs time to warm up and cool down, and that can actually take several milliseconds. So you can see two response diagrams here. On the left side, it's quantum dots. The x-axis is milliseconds. When plotted on this timescale, you can see that the response of the blue, green, and red channels is essentially a square wave in this case. So this is for quantum dots. If you compare that to KSF phosphor, on the right, you can see that the blue backlight responds very rapidly. The green phosphor is actually capable of a fairly rapid response as well. But the KSF phosphor on the time scale of milliseconds is something that you can see grow in with time and then decay with time. So milliseconds is actually something that's perceivable to humans. It's not just a measurement that you see on a graph. If you see these displays in person, you can see that there are effects. So one of these I was going to highlight has to do with the movement of images that are white. So this particular example here has to do with the movement of a soccer ball across the screen. If you look at individual frames of this display, you'll see that in the forward leading edge of the soccer ball, you'll actually see a cyan image of the ball, and that's because you're seeing photons from the blue and green channels. And then the trailing edge of the moving object will appear quite red, and that has to do with the decaying emission from the KSF phosphor. So this is a particular example of a white object moving across the screen. It's also very apparent in text applications. So if you see web pages or scrolling, like digital books, you can also see ghosting effects from slow response times from phosphors. So if you'd like to be your own scientist and see this, partially you can see this at our booth, but there are also demos that are available where you can put these on a display that you have. So there are particular websites that you can go to. I've linked them in the PDF. You should be able to access that. And you can see on your own device if you see these ghosting effects or not, depending on what's in the system. You can also, again, stop by our booth. We're going to have live demos, both the full display level, so things like this, but also on the component level. If you just look at the phosphor sheet itself, you can see by eye essentially trailing emission on the phosphor sheet. So these are the three properties that are most important to creating really good displays from quantum dots. The next section that I'm going to move into are what types of quantum display technologies are actually in existence or in study today. So Nanosys has done a lot of innovation to be able to produce these products. Product implementation is something that's as difficult and challenging as designing the quantum dots themselves. So at this point, with the acquisition from Shoei Chemical, we're definitely as committed as ever to the future of quantum dot display and the technical advances required to achieve this roadmap that I'm showing here. So starting back in 2013, again, you can see the initial launch of photoluminescent applications, QDEF, and then ultimately XQDEF, which is here. XQDEF removes the need for gas barrier protection on quantum dot film and plate products, and it lowers the cost of quantum dot color, which can enable the launch of these wide color gamut experiences into mainstream displays. So this bottom portion here of the roadmap has to do with photoluminescence. If you move up, we consider these applications to be photoemissive, so they still rely on excitation from a higher energy photon and down conversion to lower energy colors. But the emission happens on the direct pixel level instead of broadly in an LCD in these lower photoluminescent applications. So some of these types of displays that you'll see coming out in terms of technology are color conversion from quantum dots on direct pixels again. These can either be blue OLED pixels or slightly further in R&D, color conversion on micro-LEDs. Obviously, the ultimate goal in this roadmap is electroluminescence from quantum dots. It would capture all of the best optical performance of quantum dot technologies, but would remove all limitations on the form factor. So you could imagine complete flexibility in terms of the display format, in terms of flexibility and rollability and foldability. So I'm going to describe each of these technologies in more detail. So going back in history, even before QDEF, a step back again in time, QDEF was the first breakthrough performer in the commercial space, but before QDEF there was actually another idea. So the idea at first was something known as quantum rail. And this came from a time period where direct emission from the blue LEDs was not as common. In displays from before, most of these were what's known as edge-lit. So the blue LEDs or white LEDs were located on the side of the display, and then the light was moved through light guide plates and reflective sheets into the rest of the display. So then the initial concept here was to convert these blue LEDs on the side into the full spectrum, blue, green, and red, using quantum dots in polymers filled into these precision 200 micron capillaries that could actually be hermetically sealed at each of the edges. So this was the first commercial concept. And it was, in fact, possible to create many, many perfect devices out of this system. But ultimately, the defect rate and color uniformity from doing color down conversion from blue to green and red in this way was not a good match for industry at the time. So essentially, there's a zero tolerance for defects in the display industry, and it was difficult to achieve perfect color uniformity in the system. QDEF was, in fact, the first very successful commercial application that came from quantum dots. And what this is structurally is a film, typically PET or polyethylene terephthalate on the outside, with quantum dots on the inside. So this has been a program from Nanosys all the way from 2010 to today. Continuous improvement to be able to make QDEF for every potential size of LCD display. The most obvious advantage you can see with QDEF in a display, if you have a side-by-side comparison, is the really high, the wide color gamut coverage that you can see with quantum dots. Again, if you pair that with the correct color filters, you can have 90% coverage of BT2020 color space. And not only that, it overcame all of those other issues that I was describing before. So color uniformity and defects were no longer an issue. If you consider lateral uniformity within a piece, or if you consider part-to-part variation from one film to another, the difference in color space is less than 0.005, which is imperceptible. So it really met those quality requirements that were required in the display industry. The initial uniformity is one aspect of this, but obviously the operational lifetime is another. These products were incredibly long-lived and super bright. These are at the very top of the industry standard. In terms of the structure, again, typical films are on the order of about 0.3 millimeters. They contain plastic films, typically PET, with barrier layers coated on the outside of those. So the barrier layers are there to protect the quantum dots operationally from ingress of moisture or oxygen while operating. And again, if you want to see this for yourself, you can stop by our booth. We actually have one of the original articles from 2013, and it is glowing just as brightly as it was when it was made back then, if you would like to see it as a step back in history. So in terms of implementation, it's not just the color, the brightness, the reliability. To actually be successful in terms of a commercial application, it had to be easy to adopt. So if you look at the expanding schematic diagram that I've shown here, the beauty of QDEF is that it could just be easily incorporated into the existing display stack. So QDEF as a film can sit right between the blue backlight and the diffuser plate and any of the brightness enhancement films that you have in the system. So it was really easy for display makers to incorporate QDEF into the system to gain that color and brightness without challenges to their manufacturing process. So leveraging an already existing $240 billion LCD marketing infrastructure, the release of QDEF was super popular, and it breathed new life into the LCD industry at the time. It brought them back up into the premium market and was a huge commercial success. Some of the products that you'll see now with QDEF have to do with QD Mini LED. So QD Mini LED is one of the newer display technologies that's out there. Compared to traditional LCD TVs, Mini LED backlights increase the number of backlights that are there. It increases the number of local dimming zones, the contrast ratios improve in the display, and the absolute brightness can also be higher. Overall, based on consumer demand, the entire industry is moving towards brighter displays. Some of this is even at the cost of power consumption, that's such a sort of strong force from consumers out there. And if you consider these mini LED TVs that are out there today, 100% of the market has QDEF penetration in there. So every mini LED TV that's out there is containing quantum dots, that it's the perfect pairing of brightness and color that's out there. Moving beyond QDEF, the next thing that we've worked really hard on are designing air-stable quantum dots. So as I described before, in the construction of QDEF, there are metal oxide barrier layers that go on the outsides of those films. One of the exciting applications, if you were to imagine quantum dots that didn't require those barrier layers, is something that's coming out on the market now known as QDP, or quantum dot plates. And the exciting thing here is that this can combine the functionality of the diffuser plate, which I already described as being in the device stack, with the color that comes from QDEF. So it can simplify the device manufacture even further, and it can also decrease cost here. And the market currently is incredibly cost conscious, so any of these changes are super advantageous. QDP is out there, and it is on the rise. The advantages, both in simplicity and cost to manufacturers, are bringing QDP to the broader display market. It was the winner in 2022 of the Display Component of the Year. And it's the combination of the air-stable quantum dots with a diffuser plate process from our partner. This is Nantong Changed New Material, or CYD. So you'll see millions of these units now shipping from Tier 1 brands, and it's really poised to take over what I was talking about the rest of this mainstream market that is not yet being addressed by wide color gamut displays. So beyond photoluminescent technologies, we're now moving into these photoemissive technologies. The first here is quantum dot color conversion. And previously, if you go back about 5 years ago, people considered quantum dot televisions and OLED televisions as completely separate technologies. But today, it's actually possible that you compare these two pretty seamlessly. And in this context, it's color conversion with quantum dots on blue OLED. So if you pair these two technologies together, you can combine the best of both worlds. You can have perfect viewing angles, the black levels that come from direct emission from the LED, and the full color volume that's possible with quantum dots. If you talk again about efficiency in the system, QD-OLEDs can replace inefficient and wasteful color filters and also remove white subpixels from white OLED TVs to improve the energy and wall plug efficiencies of those systems. Lastly, QDCC is not just something that your consumer can see in the final display. It's something that can, again, ease manufacturing. So it's really easy for the display manufacturer to adopt. There are a lot of different ways in which color conversion could be implemented. The first, again, as I described, is quantum dot color conversion on OLED blue pixels. And this is something that's out in mass production right now. You'll see it in products, in TVs and monitors. And then looking further down the road, there's a lot of interest and a lot of research right now from many different companies, both startups and larger institutions, looking at quantum dot color conversion on micro-LEDs. And there's a couple different ways in which this could be implemented. There's what people traditionally think of, which is color conversion directly on blue micro-LEDs. But there are also companies which are working on color conversion in all three color channels, so conversion to red, green, and blue on a higher energy UV wavelength micro-LED. So this is also a possible implementation that's out there. Quantum dot color conversion as quantum dot OLED TVs is absolutely out there on the market. It's being really, really well received. There are a number of televisions receiving really high ratings that are out there. This is very recently from the end of last year. And they are really considered some of the best televisions that have come out so far. Again, combining the color volumes of quantum dots with the black levels and display angles of OLEDs. So this is really out there and popular. You'll see a lot on the display floor once it opens. Yeah, so I hope you get to see some of those as they come out. Again, it's not just about the consumer seeing the image from the television. QD color conversion on micro-LEDs could solve a really key challenge for micro-LEDs. And what this is that micro-LED is on the rise. It's on the rise for many potential future display technologies. If you consider small format displays, people are interested in micro-LEDs because the resolution that you can get from those small pixels is really high. But people are also interested in larger format displays for micro-LEDs because of the potential cost savings from smaller epi areas. So it's really an area that a lot of manufacturers are looking into. But unfortunately, if you consider the size of the micro-LED shrinking, the efficiencies often go down, and this problem is particularly bad for the red microLED. With color conversion from quantum dots, it's actually possible to do patterning directly on microLEDs with really high precision and uniformity. And with patterning, red quantum dots can be put directly onto the blue LEDs and achieve efficiencies 10 times better than just the comparative red microLED. So going from red microLED trying to use direct emission from a solid state emitter to a quantum dot down-converted red on a blue microLED, the increase in efficiency is an order of magnitude in that case. So in terms of conversion efficiencies, there are two different ways that you can consider this. The first of these is what we've been talking about for the most case of these, which are internal quantum efficiencies. So these are things like quantum yields. The other way you can consider this, especially for QDCC, this is an important aspect of the technology, is external quantum efficiencies. So it's not just of all of the blue photons which get absorbed, how many get turned into green and red, but in this case, it's of how many blue photons are incident, how many are turned into green and red. So there are a lot of materials considerations that go into making quantum dots which work well for this type of application. So the first most important thing here is the optical density of the photoemissive layer. So if you consider layering these green and red quantum dots on top of a blue LED, it's really important that your material first absorb the blue photon that it's seeing. So practically speaking, there are a lot of different ways that you can modify the optical density of a photoemissive layer. Some of these are shown in these graphs here. One is you can vary the thickness of the color conversion film that's on top. The other is you can vary the loading of quantum dots in that layer. There is an ultimate cap to how many quantum dots can go into a layer. It's actually the packing of spheres would be the absolute limit of how many quantum dots could go into a layer. And the last is almost all of these films contain scatter in addition to quantum dots. So there's an impact to the optical density that you can achieve by varying the scatter in the system. For both of these, optical density does improve this external conversion efficiency, but in all cases, there is a limit. So particularly here, I'm showing graphs of if you increase the optical density of a color conversion film for red and for green, you can see that your external conversion efficiency, or your PCE in this case, increases as you increase the optical density, and then it reaches a saturation point. So in and of itself, it's important to attenuate all of the blue light, but you also need to balance between the efficiency and the color gamut coverage in QDCC. The way in which we can control the amount of light that's absorbed, again, has to do with how we make these quantum dots and what they're made of. So if you consider, again, that quantum dots are not single component materials, but are made in layered structures of multiple materials, you can imagine that each component of your quantum dot has an inherent amount of light that it's capable of absorbing. And as you build up each of these layers, the final quantum dot absorption properties are a combination of each of those individual contributors. So altogether, it's important to build a structure which absorbs light efficiently to maximize that external quantum efficiency that you have in your final device. In terms of materials that we're working on, most people working in this space are interested in heavy metal-free applications. If you consider indium phosphide-based materials, the levels of conversion efficiency are very high for red. Again, this has to do with the conversion of blue light into green and red. If you look at the absorbance spectra of green and red quantum dots, you can see that at blue excitation wavelengths, the absorbance of red quantum dots is quite high, which means that it's possible to capture the majority of those incident blue photons and convert them into red. For typical green indium phosphide materials, you can see that the inherent absorption is lower. This is if you were to control the concentration of the two materials to be the same between green and red. And what that means is the absolute conversion efficiency of the film is somewhat limited. So there are obviously ways to get around this in terms of display manufacture. There are color filters that you can put in to improve the state of the art. But we are also looking at this from the materials perspective again, and we are looking into innovative new materials which could maintain the wavelengths, not use heavy metals, but also increase the absolute absorption efficiencies of the system. So if you look at a new composition of green that we're working on, it actually has even higher absorption properties than the green and the red. You can see this both in its absorbance spectra, controlled to be at the same concentration, or in films of the material. And with that, it's possible to create external conversion efficiencies as high for the green as it is for the red. So this is something we're super excited about, and something which can be adopted in future rounds of these quantum dot color conversion applications. So again, moving to the highest level of that roadmap that I was showing earlier, the two lower levels were photoluminescence and then photoemissive, so direct on pixels. The highest category of type of application which you could have from quantum dots is if you had direct luminescence, electroluminescence from the system. So schematically, if you go back to these energy diagrams, in photoluminescence, you would have a high energy photon come in, create your excited state, and then radiative decay to emit your light. In electroluminescence, you would have direct injection of charge into the system. So you have current that's flowing in, a cathode and an anode, and then those injected charges, your electron, your hole, would recombine to create that emission. Electroluminescence is the paradigm for quantum dot emission. The most important thing is it would be the absolute most energy efficient method of producing illumination from the system. And the other is, again, what I described before, that you could have a variety of display types, that your format is not limited with electroluminescence. Quantum dot electroluminescence can be considered as similar to organic LEDs. The fundamentals of how they operate are very, very similar. In both cases, they're diagrammed. On the left, you have an example OLED device stack. On the right, you have an example quantum dot device stack. In both of these cases, you need to make electrical contact. And in the very center of the device, you have the emissive material. So colored in pink in the center of each of these would be your either organic or inorganic emitter. But there are also differences to these. So particularly the energy levels at which you need to inject charge are different for quantum dots than for organic LEDs. And because of the nature of how charge can move into the system, there need to be special considerations to the other layers of the device stack for how you actually get charges to move into the system. A lot of this was covered in the first half of this. The most important thing is that you have high efficiency from your device. The combination of your internal quantum efficiency and your outcoupling is how you get your full external quantum efficiency in the system. Quantum dots have a lot of potential advantages here. So internal quantum efficiency for quantum dot LEDs can be considered as comparable to PHOLED or photoluminescent OLEDs, which are the highest class of organic LEDs that are possible. And again, the nature of quantum dot emission, that polarizability, can be harnessed in quantum dot LEDs to increase the efficiency of light extraction. So it is indeed possible to have higher efficiency devices from quantum dot LEDs. So obviously there are new materials challenges that are required for designing around quantum dots compared to organic emitters in LEDs, but they have a lot of potential advantages. Being an inorganic material, they have superior stability and efficiencies and potentially lower costs. So there's really a lot of reasons to continue pursuing this. So for a long time, it's been a research project. It is not yet in commercialization, but it's getting closer and closer. QDEL is a super important part of our technology roadmap, that we really think that this is the ultimate method of gaining emission from these materials. And typically when we talk about these devices, each color of quantum dot needs its own study and optimization, both for the material side, but also for the device side. And blue quantum dots have always been the area of the greatest concern. And this is something true of all electroluminescent materials. This is not unique to quantum dots. It's true for the organics also. And the simple fact of the matter is that for blue quantum dots, your band gap is the widest compared to green and to red, which means that in the excited state, first of all, you have a very high energy level of the charge that you're injecting, which means that it is more possible, and there are many other choices for it to transfer to other acceptors in the system. So basically, just the nature of where that energy level is creates the challenge in the system. What I wanted to highlight here is that we're super excited. Blue has been the greatest challenge for the longest time. And there have been some really exciting results from our collaboration with Sharp Corporation on this topic. And there have been innovations both on the device architecture side, so what is actually going into these different layers of the structure, and on the quantum dot composition and encapsulation that have led to some real breakthroughs here. So in terms of where these materials stand right now and the breakthroughs, first of all, on the graph on the left, this is a graph of efficiency as a function of year for blue materials. These are courtesy of Sharp Corporation. For cadmium-based materials in one of these lines, and then for cadmium-free materials here, breakthrough in this paper that's coming out now, the highest possible efficiencies, these are 21%. This is on par with what's possible with cadmium-containing materials, so super exciting. And then again, as important as efficiency is the lifetime of the product that you make out of this. Based on these new developments, the lifetime of this device now has a half-life, so to LT50, half of the initial emission efficiency, of over 100,000 hours. So this is even surpassing cadmium-based quantum dot records at this point. So again, just like for quantum dots, flasks in a lab are one thing, full-scale commercial products are another. The results that are showing you are not just devices in the lab. Sharp is also demonstrating really amazing display prototypes. These are based on QDEL, and these have been highlighted previously last year at SID, this year at CES, and again this year at SID. So I really recommend that you go to check some of these out. In terms of how you actually make these devices at the mass market scale, there's more than one way in which you could pattern the pixels. For quantum dots specifically, you could use either photolithography or inkjet printing. Both of these have the capabilities and the capacity to address the TV market, which is really important. So again, Sharp is sharing some of these results in a technical symposia. This is on Tuesday at 4:20. Highly recommend attending if you're interested in this topic. So this is the status of where quantum dot display is right now in terms of the market, which products are using different applications. I wanted to talk next about where do we stand in terms of what challenges there still are for quantum dots. And again, this is from the perspective of a chemist in R&D. So new products are exciting, materials properties are exciting. Something that people don't talk about very much, but is actually some of the hardest work to achieve, has to do with reliability and product lifetime. So having it work is one thing, but having it continue to work over time when it's actually out there is another. So it's really what makes or breaks a product out there. In terms of how you do this for a product, I've outlaid it here in this schematic. You would first have to define for your product what its specifications are, what are standard and extreme operating conditions that your material might see in there. You would need to test that your material can survive in all of those different cases. So this would have to do with what tests you build, testing chambers, optical measurement systems, how you actually collect and database and model that information, which moves into the modeling that you need to form a fundamental mechanistic model of what is actually happening to your material and product out there. And this happens as a function of looking at these different operating conditions, seeing what happens functionally to the degradation, building these predictive models. And all of this would happen iteratively to be able to produce products that have the absolute highest quality lifetimes. So this is something that's very fundamental to the work that we do. We really care about what types of mechanisms of degradation happen in our materials. So that's something I wanted to touch on next. So for quantum dots, there are a couple different types of mechanisms that you could imagine which degrade their performance. So when they're first made, we have their peak wavelengths, we have their full widths, they have quantum yields that are almost 100%. But over time, as they operate either photoluminescently or electroluminescently, it's possible for them to lose that emission efficiency. So from many years of work, so from decades of these studies of quantum dot reliability, it's possible to identify a few broad mechanisms of how the quantum dot can decay. So first of all, these two at the top here, which I'm calling mechanisms A and B, occur under conditions of photoluminescent excitation, and their degradation rates can vary mathematically with how they accelerate as a function of the excitation flux. So both of these follow fundamentally similar pathways, which is that you can have your carriers, so your electrons and your holes, And it's possible that they actually ionize from the quantum dot and leave the system. And when they leave the system, it's possible that they do photoreactive chemistry, so either photooxidative or photoreductive chemistry. And both of these are potentially permanently damaging to your material system. The last mechanism that I've highlighted here has to do with a lot of this work that we've done on making these air-stable quantum dots. So if you have a quantum dot operating in an ambient environment, not only is it possible that your charges can ionize from your quantum dot, they can leave. If you have species like water or oxygen present in the nearby surroundings, they can actually be activated by those charges that are ionizing. So those activated species are typically radicals. Hydroxy radicals are particularly aggressive, and those can really accelerate the degradation of your quantum dot. So these are the types of mechanisms that we consider of what might happen to the material as it's out there operating. Some of these have to do with fundamental studies. I had mentioned on this chart here about the functional form of the degradation as a function of excitation flux. So some of this is how we identify and characterize what is causing this degradation model. So if you look at the lifetime or how long the material performs, sometimes we'll characterize these as the LT50 that I described for the QDEL devices, or in this case, it's a T90, so a time until it reaches 90% of its original performance. And you can see that the functional form of how these material lifetimes depend on excitation flux can depend with different mathematical fits depending on the type of flux regime that you're in. So this is something that we use to differentiate between those first two mechanisms that I was describing. Under perfect operating conditions, this is what the model looks like on an energetic diagram. So for radiative decay, again, you have excitation from a high energy, you have thermalization to the band edge, and then you have radiative decay to emit your desired photon. In cases where your quantum dot is not emitting light, typically it is following a pathway that looks more like this. So you still have the same excitation event, you still have the same thermalization to the band edge for your carriers, but you've introduced a different decay pathway. Typically this is through a defect state. And while this defect state is there, every excited state that you make, instead of emitting a photon, decays non-radiatively, typically releasing that energy as heat instead, and what's known as non-radiative emission. So how does the quantum dot actually enter this state of being non-emissive? Again, this is a schematic diagram of what I was describing in terms of charge ionization from the operating quantum dot. So if before the material emits, when your electron and your hole are sitting there at the band edge, it is possible but very, very rare for one of those charges to become ionized, so to actually leave your quantum dot system and go to a different acceptor that's out there. It's incredibly rare, but your quantum dot goes through trillions, if not more, excitation events. So it is possible when this happens that it can lead to this charge ionization. There are a number of considerations that you can take from the material side to prevent this. Some of this has to do with spatial confinement of your excited state in the quantum dot. So again, this has to do with the building up of core shell structures and the ligands that you choose. Another element that can dictate whether this happens or not is the radiative lifetime of the material. So the less time it spends sitting there at the band edge, the less opportunity you have for those charges to ionize from the system. And then the last consideration of whether this happens or doesn't depends on the relative energetics of what is out there in the system, what sorts of acceptor species are present out there in the surrounding environment of the quantum dot. So once that charge ionizes, it leaves behind a quantum dot that is missing one of its carriers. So it leaves behind something that we call a charged quantum dot. If it was the hole that ionized from the system, it leaves behind a negatively charged quantum dot. And if it was the electron that ionized from the system, it leaves behind a positively charged quantum dot. And the important thing here is that the quantum dot, which is charged, is not necessarily permanently damaged or off. For the period it remains charged, you will not get any more emission out of the system. You'll create a non-radiative pathway for it to undergo energy loss, but it is temporarily non-emissive as long as it is charged. More concerningly, that carrier that was ionized from the system can now move through your surrounding environment and actually go on to do what I was describing as that damaging photochemistry. It can either do photoreductive or photooxidative chemistry, depending on which carrier it was that was ionized. And it is those oxidative reactions which can ultimately damage either the organic ligands on the surface or ultimately the inorganic structure itself to create a permanently non-emissive quantum dot. So all of those mechanisms that I was describing are something that can happen under photoluminescent excitation, so under low flux applications. But as we're looking forward to future technologies, one of the things that we're doing is many people are considering increasing the flux levels of displays. So right now, I already told you for QDEF under these typical, and QDP under these typical operating conditions, operating lifetimes are between 30,000 and 100,000 hours. These are top of the end components. They are longer lived than other aspects of the display. But if you're talking about moving to higher flux levels, suddenly there are new mechanisms and new degradation models that we need to consider. So why are people moving to higher flux levels? Partially, it's this consumer demand for brightness. That would increase the flux level a little bit, but if you consider further looking into the future, people are looking at AR and VR, and to be able to display true HDR content, some peak brightnesses in the system would need to go up as high as 20,000 nits. So these are incredibly bright, and for those applications, it is possible that you would need to increase the flux level significantly. So this is on the order of magnitude. In terms of actual display flux levels, if you consider right now for QDEF type and QDP type applications, the types of fluxes that people are using are between 0.1 and 1 milliwatts per millimeter squared. So when you operate quantum dots under this level of flux excitation, forming a multiply excited state in the system is incredibly rare, and the lifetimes of quantum dots are incredibly long based on the modifications that we've made for the system. If you look to the future and you talk about some of these incredibly bright displays, the types of flux levels that people are looking at for these would be orders of magnitude higher. So these could be as high as 1 to 50 milliwatts per square millimeter. So suddenly, when you reach these flux levels, there are new considerations that come into play for what happens to the quantum dot, and one of those is that multi-exciton states can form. So on this graph here, I'm showing the likelihood that something known as a biexciton in your system forms. So it's something that we haven't discussed yet. So what is a biexciton or a multi-exciton in the system? So what I've described so far in terms of photoluminescent applications is that blue light comes in, excites the system, you have an excited state electron in a hole, and those recombine radiatively to emit a photon. There is a period of time where your excited state is there, and your charges are sitting on the band edge. If your flux level is high enough, it's possible another blue photon comes in during this time period. And if another blue photon comes in and is absorbed by your quantum dot during that time, you can form what's called a biexciton. So it's 2 electrons, 2 holes excited at the same time. And when you're in this state, it's not necessarily immediately a problem. You can recombine radiatively from that state. But what can also happen is something known as Auger recombination, where the relaxation of one of your excited states actually transfers its energy to the other excited state and generates a hot carrier. So it can contribute its energy either to the other electron or to the other hole, pushes it up to one of these really high energy levels in the system. And when it's in that very, very highly energetic state, it is more likely to become ionized. So the central problem to all of this is charges ionizing from the quantum dot. It's unlikely under low flux conditions, but suddenly when you can introduce these super hot charges in your semiconductor, there are a lot more acceptor species that are out there in the world that could accept energy transfer and lead to carrier ionization. So this is a new consideration that we need to consider in designing our materials for this. Schematically, I've diagrammed basically all of what I've just described in the last few slides of what can happen in terms of quantum dots degrading or becoming permanently non-emissive. And I've broken this down into 2 halves of the slide. The first half up at the top has to do with low flux levels. So that's when those multi-exciton states are rare. Everything in black is a pathway which does not lead to permanent damage of your quantum dot. So the majority of pathways and the highest likelihood of what happens is your quantum dot behaves normally, it emits the photons that you want, things carry on. But there are these particular cases where you have charge ionization, and they can lead to permanent damage. It is not a guarantee, it's very rare, but in those cases I have these highlighted in red. In the bottom half of the slide, it's what happens if you go to these higher flux levels. Suddenly there's a new pathway which forms. You can have those multiply excited states in the system. And again, the majority of the pathways that you can take are non-damaging, but again, you can recreate these two states where you have ionization from the system, and both of those can lead to quantum dot damage. So from the scientific perspective, in terms of research, everything that we're looking at has to do with encouraging non-damaging pathways and mitigating damage in the system. So I've highlighted on these potential pathways various things that you can do either to the quantum dot itself or to the surrounding matrix that can lead the system towards the positive outcomes and not those negative outcomes. So just an example here. I don't think I can go through all of these, but an example of one of these has to do with whether or not you form this multiply excited state. So one of the things that you can do, I described it earlier in terms of color conversion as a way to improve energy efficiency. We have a lot of control over how these materials absorb light. So for each quantum dot, we can control what's known as the absorption cross-section, or how many of the incoming photons actually get absorbed by each quantum dot. So if you would like to limit the number of multiply excited states that form in the system, it's possible to decrease the quantum dot absorption cross-section. And you can do this without damaging your total absorbance. And basically this is you can divide the workload across more of the quantum dots in the system. So each one absorbs less, but your total film of quantum dots absorbs just as much. So that's one particular example of how we can control and mitigate degradation in the system. Broken down more verbally, you can imagine a lot of different methods that we can take to mitigate quantum dot operational damage and to maximize product lifetimes. First and foremost is encapsulation technologies, that there are conditions where we are able to make air-stable quantum dots, but when you talk about some of these high flux levels, you definitely do not want to have oxygen and water present in the system, that they are incredibly good acceptors of charges, and the activated species that they make are particularly chemically damaging. So generally, first and foremost, reducing that mechanism C of environmental degradation is super important into these future technologies that we're looking into. Then you can break it down into two other categories. You can consider the immediate surroundings of the quantum dot, the organic matrix that's around it, and the formulation that you're using. This obviously varies on the application. This could be inks, photoresists, resins. But generally speaking, the considerations that you want to take are, you want really good adhesion in your system. You don't want any delamination between any of your layers. That can lead to ingress and breakdown in the system. You want very, very high distributions and homogeneity. You don't want quantum dots to be aggregated. That can lead to the energy transfer that Professor Eisler was describing before. There are a lot of considerations of what types of either gas permeation or electrical and charge transport that you have in your system. And finally, there's the absolute stability of that surrounding matrix itself. So it's not just the quantum dot, it's how the entire system lives and behaves. On the quantum dot side, a lot of this has to do with semiconductor properties. So we're controlling the light absorption of each quantum dot, the electronic structure, the perfection between all of the different layers, minimizing defects in the system. This again has to do from the chemical and material science perspective, the crystalline quality, the shape that we make the materials, whether you can make perfectly epitaxial layers between the shells and the cores. And lastly, there is also the ligand binding chemistry and compatibility on the very outer layer of that material. So again, this is from the R&D perspective, everything that we were considering. And we do this for each of our different product types. So you would design through all of these and then go through that full cyclic comprehensive model that I was describing to see how it impacts the performance and to get to exactly what it requires to reach product level. Coming towards the end here, the last section that I wanted to describe is what's coming next in the future of quantum display. I highlighted a little bit about it in terms of absolute brightness that's out there. That's definitely what we're seeing so far in terms of trends. These are commercial trends that are out there in terms of what is coming out on the market. what people are demonstrating in terms of display manufacturers at trade shows that have already happened this year, and what we're expecting to come out this week at the expo. So trends seen so far in 2024, everybody is moving to bigger, brighter, and faster displays. And this is true across a lot of different formats, TVs and cars. In terms of some of what's been highlighted already, in terms of displays that came out with quantum dots, some of the big trends that we've seen so far have to do with quantum dot on OLED, which I described earlier as a technology. You can see Samsung's newest television that came out in this line. This is their QD-OLED. The new advance this year has to do with the reflective coating that's out there. People are moving to really large format displays. So there are a couple monster demonstrations of this. One from TCL, this is a 150-inch quantum dot on mini LED TV that was demoed. Similarly, 110-inch from Hisense, also quantum dot on mini LED TV. So display manufacturers are really looking at some of these large formats, and the combination of quantum dots with mini LED are really able to achieve those really high brightnesses and high color volumes that I described earlier. Monitors are another area where we're seeing a lot of quantum dot development in new formats too. So this is an example that came out earlier this year of a bendable quantum dot mini LED monitor that's out there. There's more to come in terms of catalysts in the industry. Based on research from display chain analysts, some of the catalysts that are out there right now are new markets that leverage existing or new technologies. So some of this is AR, VR. We're seeing a lot of expansion in the automotive space. Some of the catalysts have to do with improving the quality of existing display applications, and some are looking into new form factors. Some I described before about being able to fold or move the display, and also transparent screens are something that might be coming out in the future. Specific within these catalysts to quantum dots, the three new technologies that we're focusing most on from the material side in terms of what we're working on have to do with quantum dot electroluminescence for those new form factors and those high flux levels in AR and VR. Automotive display area is definitely expanding. We're seeing a lot of interest in this. Partially this has to do with advances in self-driving, that the more drivers have the time and attention for the displays, the more important they are to the design of the vehicle. So we're seeing a lot of increased demonstrations of quantum dot displays in automotive applications. This is a particular demo of a amazingly impressive car. This is a 1,200 horsepower, 0 to 60 in 2 seconds. And just like we were excited to see QDEF on the set of Dune, we're excited to see QDEF in the dash display of this hypercar on display at CES. QDEF in these applications is subject to even tighter testing regulations than in displays. So automotive have some of the strictest and harshest quality standards in terms of operating condition. Cars can get really hot. They can operate under cold conditions. So there's really, really tight restrictions on component lifetimes of this, and we are seeing QDEF pass and out there in those markets. It's definitely a growing field. There's an entire session on this. So if you're interested in seeing more, I would recommend seeing those technical sessions during this week. Lastly, QDEL is near term in terms of commercial application. And this is something we're super excited about because we've been working on the materials and their fundamentals for so long, and it's been a challenge. So they have the optical advantages that I described earlier. They have their energy efficiency, the high contrast ratios, the wide angle viewing. They're fast and responsive. They have full color gamut coverage and full format flexibility. So really exciting to see demos coming out of these. There's been a 12-inch Yale demo earlier this year, and I think there will be larger formats coming soon. So again, if you'd like to learn the technical details of this technology, talk is on Tuesday at 4:20, collaboration between Sharp and Nanosys. And then the last thing here is that there are new format displays coming up. So AR, VR, mixed reality currently is still a small total area, but a lot of analysts out there are seeing the potential for growth. Many, many companies are researching in this space. And quantum dots really have a lot to offer here. You're already seeing quantum dots in some of these, like XR displays, from Meta. The Oculus Pro is using a combination of QDEF with LCDs. As potential flux levels going up, we are working really hard in terms of R&D to make sure that quantum dots have the properties to meet the growing demands in the space. So at this point, I'd like to come to the takeaways of the talk so far. A lot of human innovation and engineering had to come together over the last century to enable quantum dots for displays. From the fundamentals 80 years ago to come up with the idea that the size of a material could influence properties, to being able to actually make them in those liquid solutions in the lab. And then 15 years to go from those small glass flasks in labs to being able to ship to tens of millions of commercial products today. So we're pretty excited about what's happened in the last 15 years and looking very much forward to what's coming next. In terms of final conclusions for today, I'd like to leave you with, first, that quantum dots have amazing properties for displays. Large color volumes, ultra-fast response times really are important for the consumer experience of the display. The reception is huge, both on the display maker side and on the reviewer side. Quantum dot TVs are winning, and you'll see that some of those reviews that I was describing, that's not just a single quarter snapshot, and that's something that's happened quarter after quarter and year after year. So it's something that people are continuing to respond positively to. So quantum dots are amazing now, but they also have the flexibility to meet the demands of the future. From the perspective of R&D, the things we're looking at designing for are stability and efficiency in air, under high flux excitation, and also in those electroluminescent devices that I was describing. And that's work that we're doing to be able to enable next generation products and all of these future designs. I've highlighted many of the different technologies that you can come and see at our booth. Some of these are the displays themselves. Some of these are the technical considerations that I was describing. So if you want to see metrology about color volume, color rings, response times of phosphors, you can come to our booth. We're just in as you come in the main entrance to the left, and that's opening on Tuesday. Also, if you have any questions that you wanted to discuss from this talk, either this portion of it or the earlier part, I'll be there Tuesday afternoon and through most of Wednesday if you wanted to discuss any of this. So definitely thank you for your time and attention on a Sunday. I hope you learned something fundamental about quantum dots in displays, and I'm happy to take questions now after the session or at the expo. So thank you.
Thank you, Ilan. If you have questions, please come and use the microphone so everybody can hear them. Thank you.
Okay, thank you, Ilan, for the very nice and informative talk. And it's good to hear and find that both the color conversion and the electroluminescent quantum dot have been processing excellently with very big success. So my question would be for color conversion application, you mentioned about the quantum dot can be applied for micro-LED and it can improve the micro-LED's efficiency and colors and process. So I have the question about for micro-LED use, the optical density, to absorb enough blue light, and the reliability might be the most concern, at least from my understanding, for micro-LED application in QD. So what's your point of view? Do you think the reliability is ready enough? And do you think the optical density can be further improved, or is it sufficient for micro-LED use?
So I guess in terms of optical density, there are the materials that are in existence and there are materials that we're working on, right? So for indium phosphide, for red, I do think it's high enough for most of the film thicknesses that people need. If you want a heavy metal-free green, indium phosphide is more challenging, again, depending on the thickness of the layer. So if you're designing for micro-LEDs and the dimensions come down to under 10 microns, you would also need your color conversion layer to be thin as well, at least on that order, if not thinner. So you're entering a region where it becomes difficult. It affects efficiency and it affects color gamut coverage. If it's just color gamut coverage, you can also apply color filtering. to block out blue light.
Yeah.
If you also care about efficiency, you would want full optical density coverage. We have these new materials that are in development.
I see.
They have much, much higher absorption efficiency, so they are on the order of the red in terms of ability to absorb blue light. So that's one possibility. The other possibility has to do with moving to UV excitation, right?
Okay.
So many are considering it is a possibility to move to UV instead of to blue. The efficiencies of the solid state emitter are just as good for UV as they are for blue, and the extinction coefficients for quantum dot materials are much, much higher if you move out to under 400 nanometers. So that's a possibility. In terms of lifetime, that was the second half of that.
Yeah.
It depends on your flux level, right? So if you're talking about flux levels that are close to the ranges that are currently out there, not exactly the low end, but in that order of magnitude of flux excitation, under encapsulated conditions, the lifetimes are there. If you're talking about moving multiple orders of magnitude up in flux level, I think those are still under research.
Yeah.
So,
Okay.
yeah.
Yeah. Thank you.
Definitely.
Thank you.
Yeah.
So thank you for a very good presentation. So you talked about degradation mechanisms and also some application areas. So my first question is, how does lifetime of quantum dots compare to OLED materials? And my other question is, how much do you have quantum dot usage in automotive display applications? You mentioned one hypercar, but is there any more?
I think there are more. Again, that is not I'm an R&D chemist, so that's not my main application. There are big companies that are working on that. So Harman is one of those. I personally cannot list every vehicle that is using them right now, but it is an area that is expanding.
But do you know if it is commercially in actual vehicles today, apart from that hypercar?
I believe so.
Okay.
But I would recommend you talk to Jeff Urich at our booth about that. He would know more, or attend the automotive session on that, and they would talk about the state of current. I do know that they are meeting the stress testing, which was the original concern on the topic, right? That when people were considering QDEF, it had not originally been tested under extreme temperature operation. And I do know that those are being qualified and passing. So I think that was the important jump in that field. The other was about electroluminescent lifetimes and comparing quantum dots to organic materials. They are potentially affected by the same types of mechanisms, that if you have bond damage that comes from oxidative chemistry that happens from imbalanced charge injection in your system, both of the materials can degrade. Quantum dots are under research. These levels would bring it up there, right? So the lifetimes that I was describing, 100,000 hour LT50, bring it into the commercial range. So it's something that people have been working on. No commercial product would come out without full testing and qualification to those, but it has the potential to be more stable, right? That the number of bonds that you need to break in an organic emitter for it to become completely emissive are very few, essentially one, right? That if you break a single bond in one of those organic structures, you completely alter its electronic properties. In quantum dots, the emissive core is protected from the outside. So when you talk about the types of oxidative reactions that happen, many of them are not damaging. That until it reaches a certain level of number of those reactions, the material actually continues to operate as normal. And that depends on the composition of how you design it. So the more confined you keep your excited state to the center of the material, and the less it has electronic access to any of those damaged sites, it can continue to emit perfectly even while sustaining oxidative damage, which is unique to quantum dots and not possible in an organic emitter. So fundamentally it is there, but it's obviously something that is under research.
Okay. Yeah, thank you.
Sure.
If no other questions, let's thank Ilan again for a great talk, and thank you all for coming here on Sunday, especially Mother's Day.
Okay, thank you.